Okay, so another two features of the op amps that we need to actually discuss before actually wrapping up the introduction to op amps and going to the examples is the input and output resistance of an op amp, right? So what do I mean by that? Let's first talk about the output resistance and then we'll talk about the input resistance. And before talking about the output resistance of an op amp, let's talk about the output resistance of a voltage source. Why? Because remember that we said an op amp is basically the voltage characteristics of an op amp is V out being equal to A times Vp minus Vn, right? So Vp minus Vn. If you look at this, it is apparent that this is basically, we can actually even define an op amp as a voltage controlled voltage source. Why? Because basically what it does is that it takes a voltage, the difference between these two, and then it generates another voltage that is, well, linearly proportional to the difference between those two voltages with a coefficient called A, right? So it's basically controlled by the difference between Vp and Vn. So it's controlled by a certain potential difference, and it is a voltage source because it generates a voltage at the output that only and only depends on the two inputs. So if I have this, for example, if I have this op amp and I connect I don't know, 3 volts here, and or let's make them real a little bit. Let's say 3 millivolts here, and I have 2 millivolts there, right? And the gain of the op amp is 1000. I'm gonna have a 1 volt here, right? And it doesn't matter if I connect a resistor here to ground, if I connect, I don't know, a bunch of resistors with a voltage source, like let's say something like this, or like another current source here. It doesn't matter what do I connect to this node. It's always going to be 1 volt because it's the output of the op amp which is controlled by the two inputs. That is the definition of a voltage source. Remember, we defined a voltage source, dependent or independent. A component that it sets, enforces, or sets the voltage across it no matter what is it connected to. It doesn't matter what you connect the voltage source to, what kind of a circuit you connect it to. You can connect it to a single resistor, or you can connect it to, well, a circuit like this, right? The orange circuit here. It doesn't matter. It always sets the voltage independent of what is it connected to. Here is the same thing. So op amp sets the voltage here only depending on the difference between these guys, right? So it's a voltage controlled voltage source. That's why I want to talk about the output resistance of a voltage source first, because op amp is more or less a voltage source. It's a dependent voltage source. Okay, so what is special about a voltage source and its output resistance? And what do I mean by output resistance? Output resistance is if I look into the op amp, if I look into my voltage source. So let's say that I have a voltage source 5 volts, right? For a voltage source, the output resistance is also called internal resistance, right? So ideally, my internal resistance is 0. So if I connect this voltage source to, let's say, a 5 volt, a 5 ohm, or, well, any resistor, let's say 17 ohm or like 10 ohm, right? Doesn't really matter. If I connect it to a resistor, you know immediately that if I define these two points as ground, here's always 5 volts, right? Why? Because I have a voltage source there, right? So this is basically ideal voltage source. Now, what happens in real voltage source? So now imagine that my voltage source has some internal resistance. Let's say that it is 1 ohm, right? Very small, but it is there. It's not 0, right? So if I draw the box around the whole thing, so this is my voltage source, whatever is inside the dashed box. Now if I connect this real voltage source to the 10 ohm, what would be the voltage here? Well, I have a resistive divider. We know how to solve this. So here, V is going to be 10 divided by 10 plus 1 times 5. So I have 50 divided by 11, a number that is definitely less than 5. Okay. That's not nice. It's still very close to 5, but it's not good, right? It's not exactly 5. It gets even worse if instead of 10 ohm, so it's not only it is not precisely giving me the voltage that I have. Imagine that instead of 1 ohm, I connect, instead of the 10 ohm, I connect it to another 1 ohm, right? Same real voltage source. What happens to that V? Well, V this time is going to be 1 over 1 plus 1 times 5. So it's 2.5, not even close to that 5 volt, right? So these two cases are real voltage sources. So now you can imagine that for a voltage source, ideally, I like the output resistance to be 0. And the reason is that if it is not, then we're going to have problems. The voltage source is not going to be the voltage source that I know, because the voltage source that I know always makes sure that the output of the voltage source is always 5 volts. But in this case, if I have an internal resistance of 1 ohm, it depends on what I connect to it, right? It's not like always like, yes, if I had 1 mega ohm here, so let's say the same voltage source with 1 ohm internal resistance, but this time I connect it to, let's say, 100 kilo ohm, some large voltage, right? So now what would be the voltage here? Well, V is going to be 100,000, so 10 to the power 5 over 10 to the power 5 plus 1. That's pretty much 5 volt. Oh, sorry, times 5. So that's pretty much 5 volt, because the fraction is pretty much 1. So you multiply 1 by 5. So depending on what do I connect to it, it is going to give me different voltages. That's not a good voltage source. So ideally, in reality, we do have a little bit of internal resistance, to be fair, right? And that is very tricky to design a voltage source that doesn't have, like, basically the trick for a voltage source, one of the most important parameters for a voltage source is that to make sure that the internal resistance or the output resistance, the resistance that we see at the output of the voltage source, is pretty much 0 or it's minimized, right? So depending on if I know that this voltage source that I'm going to use is going to be connected to all big resistors, I don't mind. I'm going to be okay with it, right? I'm going to be okay with even 10 ohm or like even sometimes if I'm connecting it to a mega ohm kind of resistors, then I'm going to be okay with the internal resistance of even like 100 ohms, right? But if I know that I'm going to connect this thing to a bunch of small resistors, then this voltage source better be really, really, really ideal, right? So now for an op amp, because the output resistance of an op amp, meaning that the resistance at the output of the op amp, so the resistance that I see if I look into the op amp from the output, if I want to basically what this orange circuit sees to its left, right? So it doesn't see an op amp. Like if I want to model the entire thing inside this circle, oops, I went too far. So the entire thing inside this circle, when I look at it from the point of view of the orange circuit, I'm gonna, like, if I want to replace this entire green circle with this resistor, I'm gonna call that the output resistance, or R out, right? So output resistance of an op amp should be ideally 0. Okay, and we just talked about why and the rationale for that. Now we're ready to talk about the input resistance. So like, what do I see from the input? Okay, so now let's talk about the input resistance. So to discuss the input resistance, first let's consider this circuit. So let's say I have just a simple voltage source. Let's say the voltage is 9 volts, and I connect 3 resistors in series to this voltage source, and then it goes to ground again. And let's say each of these resistors they're all equal, so 5 ohm, 5 ohm, 5 ohm. Okay, and what I want to do is to take the voltage across this middle 5 ohm resistor. So basically this voltage, let's call it Vx. Okay, I want to take this voltage and amplify it to whatever I want, right? Amplified by a certain number, right? So if I want to connect this to, if I want the voltage difference to be amplified, let's say I connect it to the amplifier, the op amp, and here's my V out, right? So if I do this, now remember when I wanted to actually measure a voltage across a resistor with a voltmeter, the most important feature of the voltmeter that I mentioned was that its internal resistance has to be infinity. Why? Because if the internal resistance, imagine that this is like the entire thing here, I'm going to replace it with the resistor, right? If this resistor is anything but infinity, my circuit on the left, the initial circuit that I had, is going to change, right? Initially, like I want ideally this voltage to be the Vx. If I don't connect this amplifier, I want the Vx to be 3 volts, right? Because it's 3 different resistors. The voltage 9 volt is going to be distributed equally among these resistors, so each of them will get 3 volts, right? But what happens is that if the resistance of this amplifier, if the resistance equivalent to the circuit inside this green circle is anything other than infinity, then I'm going to end up with something like this. 9 volts, and then resistor, 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 and I'm going to have that resistance here, right? And if this is 5, let me use the same color. So this is 5, this is 5, this is 5, and if I replace this, let's say if this is, I don't know, 100 ohms or 200 ohms or 1 kilo ohm, it doesn't matter if it's a small or large. As long as it's not infinity, it's going to be in parallel with this 5 ohm in the middle, and I'm going to have a different resistance, right? So my circuit is going to look like this. So 5 here, 5 there, and here I'm going to have 5 in parallel with, let's call this Rx. So the voltage that I was interested in is going to be anything other than, something other than 3 volts, right? So Vx is going to be 5 in parallel with Rx over 5 plus 5 plus 5 plus 5 in parallel with Rx. This is not 1 over 3. How could it be 1 over 3? Well, if Rx was infinity, therefore 5 in parallel with Rx would have been 5 times infinity over 5 plus infinity. 5 plus infinity is pretty much infinity, and 5 times infinity over infinity is going to be 5. Okay, so that is the only case that, so I can say then Vx would be equal to 1 over 3. Anything other than infinity, it's not going to be basically resulting in a good thing for me. So this tells me that if I want to sense this, any voltage, and amplify it, because it's a voltage dependent voltage source, right? Remember, this op amp was a voltage dependent voltage source. So I had a Vp and I had a Vn and I had a V out here, and I was saying that V out is equal to A times Vp minus Vn, right? So basically I'm sensing the voltage difference between Vp and Vn, and then I'm amplifying it and generating this V out, right? When I'm sensing something, it's like kind of like measuring something, right? I'm measuring the voltage across something, and then I want to amplify it. And I know that if I want to do a proper measurement, the internal resistance of my voltmeter has to be infinity. In this case, the internal resistance of my voltmeter is the resistance that I see to the input of my amplifier. So this Rn has to be infinity if I want to do a proper job of amplification. So to summarize, for an ideal op-amp, Rn has to be going to infinity, Rout has to approach 0 if I want to have an ideal op-amp, right? Of course, in engineering, when we say infinity, we mean like large enough, orders of magnitude larger than well, whatever other resistor is in our circuit, right? So for example, in this case, we have 5 ohm, 5 ohm, and 5 ohm. If the input resistance is in the order of hundreds of kilo ohms, that's pretty much infinity, because imagine that, like, if I had here, so infinity is, or really means orders of magnitude larger. So in this case, for example, imagine that instead of basically the input impedance was 100 kilo ohm, so 5 in parallel with 100 kilo ohm, or 10 to the 5, is equal to 5 times 10 to the 5 over 5 plus 10 to the 5. So 5 plus 10 to the 5 is 100,000 plus 5, right? Pretty much 100,000. And then you can cancel them out. This, you can actually approximate this with 5, okay? And when I say R out is equal to 0, again, it means that we saw it in the previous slide that I mean a lot smaller than any other resistor in the circuit. In that case, we saw that when the resistance that we were connecting to our voltage source was a really large resistance in the order of tens or hundreds of kilo ohm, then it was okay to have an internal resistance of voltage source to be like 1 ohm or 10 ohm, right? So that's what we mean by infinity and 0 in engineering.